This lecture is going to be focusing on the basics of acids and bases. This is Chapter 16, Acid and Base Equilibrium. In terms of acids and bases, there are two different perspectives that you can take about whether something's acidic or basic. One of these perspectives, or at least ways to view things as acids or bases, is the Arrhenius definition. Acids in this case are defined as those that increase the concentration of hydrogen in your solution, and bases increase the amount of hydroxide. If you look at the formula of HCl, you'll remember that there's an H in front, so that H completely ionizes when it dissolves in water, and then you have more hydrogen ions in your solution. Bases like sodium hydroxide, NaOH, completely dissociate, and when you have that in solution, you have Na plus ions and you have OH minus ions. So you're obviously increasing the hydroxide ions in your solution. So that's one perspective on how to define acids and bases. There is another one called the Bronsted-Lowry definition, and it has to do with proton donation. Protons are hydrogen ions, meaning H plus. Bases are those that accept hydrogen ions. One of the important things to remember about Bronsted-Lowry acids is that they have to have a hydrogen that can fall off, an acidic proton. For a base, they have to have a pair of non-bonding electrons. An example of a non-bonding pair of electrons would be water, where you have two non-bonding pairs of electrons. Now, let's actually talk about whether it can be both. If it can be both, a hydrogen donor or a hydrogen acceptor, we call it as amphiprotic. You've also probably heard the term amphoteric, and they essentially mean the same thing. All right, now let's actually talk about how protons get accepted and donated. So here's hydrochloric acid on the left and there's water on the right. When they bump into each other, this hydrogen's lost from HCl and it attaches on to water. This is what we call a hydronium ion, and that's one of the definitions for an acid. So the acid would be HCl because it loses the hydrogen, which we call a proton, and the water accepts the hydrogen, which we'd call a proton, and that would be the base. So in this case, HCl is the acid and water is the base. Don't forget, water can also behave as the opposite too. Water can also behave as an acid. All right, so let's move on. There is a name called conjugate bases. Conjugate bases are what's produced once the hydrogen has been lost. So HCl, when it loses its hydrogen, the Cl minus is what we call the conjugate base. All right. Now, here's a good example of conjugate bases and conjugate acids looking at a chemical equation. So HNO2, when it loses a hydrogen, it's now the conjugate base, NO2 minus. And water, in this case, is accepting the hydrogen, so it acts as the conjugate acid after it's accepted it. Another way is to look at it backwards in terms of what they form when you go from products to reactants. All right. Reactions between acids and bases always yield their conjugate bases and acids. Don't forget, acids become the conjugate base, bases become the conjugate acid. All right, acid and base strength. This is probably the most important thing that you're going to be writing down in these notes. What I want you to do is I want you to record down what it means when you have conjugate bases formed after a strong acid has been dissolved in water. So looking at this table up here, hydrochloric acid, when it loses its hydrogen in water, it's now Cl minus. That is the conjugate base, and that conjugate base is extremely weak, pretty much negligible according to this chart. So don't forget, the conjugate bases of strong acids are weak. You want to put a star, happy face, whatever you need to remember this joke. Moving on. Weak acids only partially dissociate in water. That means that if I have, let's say HC2H3O2. It's a relatively weak acid. We're talking about acetic acid. And acetic acid, when it dissolves in water, most of it does not dissociate. Most of it does not break off. So you basically keep the hydrogen attached to it. Their conjugate bases are weak bases still. All right, moving on. Substances with negligible acidity, things that are barely acidic at all, kind of like water, their conjugate bases are extremely strong. So actually OH minus is a better example. OH minus hydroxide, its conjugate base is extremely strong and accepts a hydrogen and forms OH minus. All right. In any acid-base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. So in this one, the stronger base is water between HCl and H2O. H2O is much stronger of a base than Cl minus, so the equilibrium lies far, far to the right. So K is not measured. One of the things that you can think about is K is our equilibrium constant, so since the products are extremely favored, K is much larger than 1 in this problem, because don't forget the equilibrium constant is the concentration of the products over the concentration of the reactants. Now, looking at this one, acetate is a stronger base than water, so the equilibrium favors the left side. What this means is that the acetate is going to be in the form on the left side, and that's why K is much, much lower than 1. As you've seen, water is what we refer to, as I mentioned earlier, amphoteric. And in pure water, a few molecules act as bases and a few act as acids. So water molecules can bump into each other, and when they do so, they form hydronium and hydroxide. This is what we call autoionization, meaning it's sort of like an autopilot. It happens automatically because they just bump into each other and they form these ions. Then these ions can bump back into each other and form 2 water molecules. Alright, the equilibrium expression for this process is the equilibrium K sub C of hydronium times hydroxide. Now it may be like, what about over H2O times H2O? And the reason that's not there is because H2O is a liquid, and we don't write liquids or solids in equilibrium expressions. That's why you see K sub C equal to the concentration of hydronium times hydroxide. So let's go back to the previous slide very briefly. Again, it's the products over the reactants, and notice the products are liquid, that's why we're not writing them down. So the equilibrium expression is K sub C equal to those 2 times each other. This is a special equilibrium constant, so we actually change it to mean K sub W. So K sub C, when it's H3O plus and OH minus, we call it KW. KW is a value that we have to remember. You need to memorize that K sub W is equal to 1 times 10 to the negative 14. It's easy to remember because, remember, the pH scale, which we're eventually going to get to, goes up to 14. So just remember, the exponent is 14. All right, so pH is defined as the negative base 10 logarithm of the hydronium ion concentration. There's the formula right there. So if you know the concentration of hydrogen ions in your solution, you just take the negative log of this. I actually prefer writing it out different. I write it out as pH equals negative log, and then I have H plus in here. You could write either. It doesn't matter. It means the same thing, because the amount of hydrogen ions you have in solution, all those hydrogen ions form hydronium ions. They're equivalent to each other. pH comes from the derived German of potens hydrogen, which is the potential hydrogen that you have in your solution. All right, in pure water, K sub W is equal to that 1 times 10 to the negative 14th, right? And then that's the concentration of hydronium times hydroxide. Because in pure water, the amount of hydronium and hydroxide ions you have are equal to each other, we can write it out as the square root of 1 times 10 to the negative 14th. And you get 1 times 10 to the negative 7th for hydronium. If you plug that in for the pH, that means that pure water, you take the 1 times 10 to the negative 7 and stick it in for the negative log, pH is 7 at neutral water. So solutions that have a pH less than 7 are acidic, solutions that are at 7 are neutral, and solutions that are above 7 are basic. And you can look at the table to see how the concentrations of hydrogen and hydroxide vary depending on the pH and whether it's acidic or neutral or basic. Take a moment to just look at the table. I would in fact pause this presentation to look at it and understand what those numbers actually mean behind the table. Don't forget, acids are less than pH because there's a lot of hydronium. Bases are lower hydronium ions, less hydrogen ions in solution, so its pH is greater than 7. All right, now, these are some common pH values for common substances. Take a look at it. Make sure you're familiar with it. It's basically the same kind of stuff that you've seen in middle school. There are other pH scales. So remember, pH, or there are other P scales. pH is the negative log of hydrogen ions. pOH is the negative log of hydroxide ions. So we can actually calculate a couple of different things. So the negative log of hydroxide is pOH, and pK, we can actually take the negative log of KW, which remember is that equilibrium constant for water, and that's pKW. So P just means negative log, that's it. So let's look at some interesting math. Watch this carefully. Because the concentration of hydroxide times hydronium equals K sub W, which is 1 times 10 to the negative 14th, we know that the negative log of H H3O plus negative log of hydroxide is equal to the negative log of Kw, which is 14. In other words, this tells us mathematically, if we get rid of those logs, that pH plus POH equals pKw, which is 14. So if you know the pH of a solution, you can figure out the POH by just doing some simple algebra. So if my pH is 3, my POH has to be 11. If my POH is 2, my pH has to be 12. So you can go back and forth between pH and POH. I would write down and really put a box around, smiley face, star, whatever it is, to highlight that last equation down on the bottom. All right, how do we measure pH? Well, we use these things called indicators. Indicators are really just not terribly accurate indicators sometimes. Like litmus paper is not terribly accurate. It turns red when you have a pH about 8 and above. Blue, it's about 5. So they're essentially just indicators to tell you what the pH of your solution is. We also like to use indicators with titrations that can give us a little bit more precise reading about the pH of a solution. One of the more precise ways we use is we use pH meters, and it measures how much electricity conducts through the solution. So remember, acidic and basic solutions, they're electrolytes, so they conduct electricity, and we can measure the voltage in that solution, and that can give us a reading that we can translate into a pH reading. We have to memorize these strong acids. It's without a doubt. You need to hit the Quizlet applet on my website, memorize HCl, HBr, so forth. These are by definition strong electrolytes, and they exist totally as ions in aqueous solutions. For the monoprotic strong acids, don't forget that H3O plus, that's all of your hydrogen ions in solution. All right, so strong bases are, actually let me go back to that. Let me explain that one more time more clearly. The reason it said monoprotic on the previous slide is that if I have HCl, for every mole, for the concentration of HCl, it's equal to the concentration of hydronium or hydrogen ions in your solution. That only changes when you deal with diprotic acids. H2SO4 is a diprotic acid because there are two hydrogens. You can't do the simple math of whatever the concentration of HCl is, your acid, is equal to the concentration of hydrogen ions in your solution, which is hydronium. Strong bases are the soluble hydroxides, which are any OH that's bonded to an alkali metal, and heavier alkaline earth metal hydroxides like calcium hydroxide, strontium hydroxide, and barium hydroxide. Now, I like to argue with textbooks when they say calcium hydroxide is a strong base, just because you see a white precipitate whenever calcium dissolves in water and you form calcium hydroxide. Calcium hydroxide is only slightly soluble. So I have a problem with calling it that, but memorize it anyhow because it is going to be on your AP test. Again, these substances completely dissociate in aqueous solution. All right, dissociation constants. For a generalized acid dissociation, and notice it says HA. The A just refers to whatever the other part of the acid is. So if it's HCl, the A is Cl. If it's HBr, the A is Br. The equilibrium expression is the following. K sub C is equal to, obviously, the concentration of your products, with their exponents being their coefficients, which are just 1 on this one, over the concentration of your reactants. And notice H2O is not written down because it's liquid. This is something we call K sub A because it's describing it for an acid. A stands for acid. Now, the greater the Ka, the stronger the acid. To understand this, let's go back and look at that equilibrium expression. So the stronger the acid, the more likely that hydrogen is going to fall off of that A. So if it's a strong acid, the A completely falls off, which means you have more products than you have reactants in terms of the equilibrium. That means this top number is going to be bigger than this bottom number. So K sub C, which we call K sub A, the bigger it is, the more acidic it is. So again, here's some examples of the acidity of various compounds. We have everything from nitrous, hydrofluoric, benzoic, acetic, and you can use their Ka values to basically identify how strong an acid is. And you'll remember that table that we saw on a previous slide. That table on the previous slide shows for you exactly which ones are strong and weak, but we just use the Ka values to make it easier. All right, calculating Ka from the pH. The pH of a 0.10 mole solution of formic acid, which is HCOOH, at 25 degrees Celsius is 2.38. you need to calculate the Ka for formic acid at this temperature. The way you approach it is what you know. You know that K sub A for this particular acid, remember you've got to write it dissociated, so you obviously, when it bumps into water, it loses a hydrogen, so actually it loses a couple, and you have H3O plus and COO minus, and then there's the original acid down the bottom, because remember the hydrogens are lost. Alright, moving ahead. So, in continuing on to calculate this reaction, you do the following. You need the equilibrium concentrations of all three things. You can find H3O plus because it's the same as HCOO minus from the pH. So what you do is you go and look at your equation, which is pH equals negative log H3O plus. pH we knew is 2.38, and then what we do is we do a little bit of algebra, which is being displayed for you right now. Don't forget how to use logs. You're seeing the math shown right now on how to figure out what the concentration of hydrogen ions in your solution is. So you know the amount of hydrogen ions that are formed now from HCOO minus. At this point, I'd like you to pause the presentation and I'd like you to look at how these steps were followed to figure out the hydrogen ion concentration. Again, the hydrogen ion concentration is this H3O plus that I have down at the bottom. Look carefully. Alright, now you can set up a table, an ice table. So you set up the ice table, you know that you begin with this acid here, and you're producing HCOO minus and H3O plus ions. Now I know it may be confusing because K sub C, you originally saw it as COO minus. Treat it as a monoprotic acid where it's only losing one hydrogen initially. So you begin with 0.10 of this, you know what the change is, and then you figure out what it is at equilibrium, look at the table and look at your given information to make sense out of it. And then you plug in your values for K sub A, and then you find K sub A. There are a number of sample problems in your textbook to look at with this, and I can also go over it with you as well. Alright, percent ionization. Percent ionization is how much does that acid actually dissociate. What you would do is find H3O plus at equilibrium, how many hydrogen ions are formed, over HA, which you started with in terms of the concentration of the acid, multiply it by 100, you got your answer. So in this example, you've got hydrogen ion concentration for an acid of 4.2 times 10 to the negative third. Then you have the acid itself, which is 0.1, and you divide those two, multiply it by 100, and that means that for this particular acid, only 4.2% of it actually ionizes and breaks apart. Alright, next problem. Calculate the pH of a 0.30 molar solution of acetic acid at 25 degrees Celsius. So we're given K sub A for acetic acid, which is 1.8 times 10 to the negative fifth. So we have to write out the equilibrium expression for obviously this one. So it's going to be the products over the reactants. And remember, water does not count. H2OL, it's not going to be in our K sub A expression. Alright, so the equilibrium constant expression gets written out like this. Then what you're going to do is you're going to set up your table. It's the same ice table that you set up previously with equilibrium, and you're assuming that X will be very small compared to 0.3 and can pretty much be ignored because acetic acid, when you're looking at how much of it dissociates, very, very, very little dissociates. It's a very weak acid. So because of that, the 0.3 minus X, it's not going to change its concentration very much at all. Very little of it. Actually, acetic acid, 98% of it does not dissociate. It stays C2H3O2H. It just stays there. It doesn't change. Alright, so now you plug in your Ka, and it's equal to, remember, the products over the reactants, and you plug in the values from the equilibrium expression in your ice table. You solve for X, and then you can figure out your pH of the acetic acid by plugging in the concentration of hydrogen ions in your solution. And pH ends up being 2.64. At this point, I'd pause it, I'd roll it back a little bit to make sure you understand the math that was done. Again, refer to your equilibrium notes from the previous chapter. Alright, polyprotic acids. These ones become a bit more tricky. These are the acids that have more than one acidic proton. So, classic example is H2SO4. That's a diprotic acid. It has two hydrogen ions to donate. If the difference between the Ka for the first dissociation and the subsequent Ka values is 10 to the power of 3 or more, the pH generally depends only on the first dissociation. What this means is that, for the most part, the second once you've lost your first hydrogen, if you have H2SO4 and you lose the first one, and if the Ka values is 10 to the power of 3 or more, it's probably not going to dissociate much further. Alright, so bases, let's talk about bases for a bit. Bases react with water to produce hydroxide ions. So this is a classic example where you can see conjugate acids and bases being labeled. You might want to pause it and look at how everything's labeled and where the proton donation is happening. In this case, it's a hydrogen leaving the water and going to the ammonia with NH3, which is base. That's why it's accepting the hydrogen. Alright, now, weak bases. The equilibrium constant expression for this reaction is what we call K sub B when we write it out like this. Don't forget we're using B as the opposite of basically Na, which is acid. K sub B could be used to find the hydroxide ion concentrations and through it pH. So, what is the pH of a 0.15 molar solution of NH3? We write out the equilibrium expression, which is products over reactants, and what we can do is we're told that it's 1.8 times 10 to the negative fifth. That's the K sub B for this, for ammonia. We can write out our ice table, although this doesn't have the change on it. And then you can set the K sub B equal to the products over the reactants, which is your equilibrium expression. Solve for x squared. And once you solve for x squared, then you know x and can figure out the concentration of your hydrogen ions, which will give you your pH. So the hydroxide is 1.6 times 10 to the negative third when you plug it into your equation. You can figure out the POH, and then from the POH, if you subtract 14, or you subtract that value from 14, you now know the pH. We'll be going over these problems in class more in depth. Alright, K and sub KB. They're related to each other with this equation. K sub A times K sub B is always going to equal K sub W. Don't forget K sub W is that 1 times 10 to the negative 14th value we're dealing with. Remember the 14 symbolic of the pH scale going up to 14. Therefore, if you know one of them, you can use it to calculate the other one. Alright, reactions of anions with water. Anions are bases. They accept hydrogen ions. As such, they can react with water in a hydrolysis reaction to form hydroxide and a conjugate acid. So if I have NaCl, when Cl is negative in water as aqueous, it can bump into water and form a hydroxide and HX, aqueous. So here's a classic example of it. Here's a cation with water, where you have a positive ion bumping into water. Cations with acidic protons, like NH4+, will lower the pH of a solution. So it's important to understand how pH is affected by adding different types of salts to it. Okay? Most metal cations that are hydrated in solution also lower the pH of the solution. Right. Attraction between non-bonding electrons on oxygen. And when you think about the non-bonding electrons on oxygen, remember there's a pair right here and a pair right here. That's why it's really electronegative on the oxygen. And the metal cause a shift of the electron density in water. This makes the OH bond more polar and the water more acidic. So water can actually lose a hydrogen much easier in this situation whenever you have that shift in electrons. Greater charge and smaller size make a cation more acidic. So the more positive it is, the more acidic your solution can be, because the attraction between that great positive charge and the smaller sized ion can rip off a hydrogen from the water, making it acidic. Alright, the effect of cations and anions. An anion that is the conjugate base of a strong acid is not going to affect the pH very much. An anion that is the conjugate base of a weak acid will increase the pH. I recommend writing these down in a table, and this is a good way to remember the effects of different salts on the pH of a solution. So let's look at this very carefully. We have a couple of different solutions down here in the bottom left we're looking at. We've got NaNO3. So let's think about what NO3 is. So NO3 is the conjugate base for a very strong acid, which is nitric acid, HNO3. So let's look at these two prompts right here. And it says An anion that is the conjugate base of a strong acid will not affect the pH, and that's why the pH of this solution when we added sodium nitrate is still 7. All right, let's look at the next one. We have calcium nitrate, and this time the pH is slightly lower. But remember, calcium has a much more positive charge than sodium, and that means it can rip off a hydrogen on water, or it can make water more acidic, and because it can make water more acidic, you have a slightly lower pH. Now we're looking at zinc nitrate, and what we're looking at the difference between calcium, zinc, and aluminum. Aluminum obviously has the greatest positive charge, so it makes water even more acidic at a lower pH, okay? So remember, cations have that huge effect because they can make water acidic. The stronger the positive charge and the smaller that atom, the more acidic your solution. And please look at your periodic table. Remember the periodic table trends for the size of ions to compare sodium, calcium, zinc, and aluminum. Because if you're comparing, remember calcium and zinc are the same exact, they're the exact same charge, but zinc is a much smaller ion because it's further to the right on the periodic table. That means that zinc is a smaller but the same charge as calcium. It's going to make water more acidic. Remember, small size of the ion plus larger positive charge makes that solution more acidic. Continuing back to the prompts, an anion that is the conjugate base of a weak acid will increase the pH. And then the last one is what I was referring to, is a cation that is the conjugate acid of a weak base will decrease the pH, which is the flask example that you've seen right here. All right, cations of the strong Arrhenius bases will not affect the pH. And when you look at this one, let's look at the cations of a strong base. Sodium is the cation of a strong base because of sodium hydroxide. Therefore, it's not affecting the pH very much. Let's look at another one. Other metal ions will tend to decrease in pH. And that's just like we saw in the previous picture, that charge and size affecting the pH. When a solution contains both the conjugate base of a weak acid and the conjugate acid of a weak base, the effect on the pH depends on the Ka and the K sub V values. Alright, this is the table that you would want to write down. I would recommend pausing this, looking at the table for a good 5 minutes and thinking about it. Don't forget, the more polar the hydrogen anion bond, and or the weaker the hydrogen anion bond, the more acidic the compound is going to be. Acidity increases from left to right across a row and from top to bottom down a group. In oxy acids, in which the OH is bonded to another atom, Y, the more electronegative Y is, the more acidic the acid. So electronegativity does play a difference here. For a series of oxy acids, acidity increases with the number of oxygens. Take a look at these ones. Resonance in the conjugate bases of carboxylic acid stabilizes the base and makes the conjugate acid more acidic. And Lewis acids are defined as electron pair acceptors, which are pretty darn close to the definition that we had for bases with the Bronsted-Lowry definition. But what they do is they essentially accept those pairs, and this is organic chemistry. You're not going to see this too much on your AP test. Don't forget, atoms with empty valence electrons can be Lewis acids. Lewis bases are defined as electron pair donors. So there's your definition of an acid and base. You really get into this when you take a course your sophomore year in college, or if you pass the AP test, this would be your freshman year in college, called organic chemistry, where you really start studying this stuff. It's really interesting because it allows you to synthesize lots of cool molecules, like everything from aspirin to LSD even. Anything that could be a Bronsted-Lowry base is a Lewis base. So the Lewis acid and base definition is very close to Bronsted-Lowry definitions. Lewis bases can interact with other things besides just hydrogen ions. They don't just rip off hydrogen ions. They can interact with things like boron triphosphate.